So in chapter 12, what we'll be looking at is we'll be looking at phase changes. So what happens when we go from a solid to a liquid to a gas, qualitatively and quantitatively. So today our main goal is if we take a certain amount of ice, say it at negative 20 degrees Celsius, and we heat it to 80 degrees Celsius, how much heat is needed. Or if we take steam that's at 110 degrees Celsius, we cool it down, how much heat is released if we cool it down to 30 degrees Celsius. So today is more of the quantitative part. Later on in chapter 12, we'll be looking at the different aspects of phase changes. So for example, later on we'll look at what happens at the boundary between the liquid and the gas phase, the liquid and the solid phase, and the solid and the gas phase. And there's different features that each one of those boundaries has. Then from continuing in chapter 12, we'll look at the forces that hold molecules together. So we're not talking about the actual bonds in the molecule, but if you imagine if you yourself as a molecule and you hold someone else's hand, that's another molecule. So two molecules are interacting. There's something that holds those two molecules together, which are called intermolecular forces. And that has a lot to do on the boiling point and melting points of compounds. So we'll talk about that as well. So lots of good stuff in this chapter. So first, when we talk about phases of matter, and when we talk about phases of matter, we're talking about in the form of potential and kinetic energy. So maybe if you remember, you might have learned in CP1, potential energy, energy stored in chemical bonds or based on its height. Kinetic energy is energy due to motion. So you can imagine the more the molecules move, the more kinetic energy it has. So when we're referring to potential energy in reference to phases of matter, we're talking about the forces that hold the molecules together, and those are referred to as intermolecular forces. So for example, when we take ice and we heat it and it becomes water, we're weakening the intermolecular forces, aka decreasing its potential energy and increasing its kinetic energy. So if I was to draw the three states of matter, say we have a solid, then it goes to liquid, and then it goes to a gas. So the solid form is the form of matter that has the most potential energy, because in the solid, as we'll see in a second, the molecules are very constrained. And then gas molecules have the most kinetic energy, because gas molecules are freely moving and there's very little attractive forces that hold them together. And so this is just a balance between potential and kinetic energy. So when we talk about attractive forces, we're again talking about forces that hold molecules together, and that's different from the actual bonds that we have in molecules. So the bonds are referred to as intramolecular forces, or referred to as bonding forces, and those are, as you see here, like this OH bond is an intramolecular force, the HCl bond, the CO bond. So all bonds are intramolecular forces. When we get to inter, we're talking about things that hold molecules together. So here we have on this left-hand side, we have the water molecules, and these water molecules are held together by an intermolecular force, which is referred to as hydrogen bonding, that we'll learn about later. But this force is like an attraction, holds all these water molecules together. So you can imagine that if this attraction is very strong, it takes a lot of energy to break the forces apart. And that's why water has a very high boiling point. It's because it has very strong intermolecular forces, causing it takes a lot of energy to break those forces to make water become a gas. But on the other hand, if we look at, for example, the components of gasoline, it takes very little energy to boil gasoline or vaporize it because the forces that hold the molecules involved in the mixture of gasoline are very weak. So therefore, it doesn't take much energy to break them. Likewise, if we look at the middle diagram, here we have methanol, and in methanol we also have an intermolecular force that is referred to as hydrogen bonding. So again, it holds these molecules together. So it takes energy to break them apart to form a liquid and a gas. Now with HCl, it's a little bit different. So HCl is a polar compound which has a positive end and a negative end. And so the positive end of one interacts with the negative end of the other. And so this is referred to as a dipole-dipole interaction. And we're going to talk more about these interactions later. I just want to introduce them. And so dipole-dipole is for polar compounds, and it's not as strong as hydrogen bonding. So something that has hydrogen bonding, and if we're comparing apples and apples, compared to something that has dipole-dipole, the hydrogen bonding would have generally a higher boiling point than the dipole-dipole. So again, all we're doing in this chapter is manipulating the intermolecular forces. So when we have this balance between potential, aka attractive forces, and kinetic energy, we get to different properties of the physical states. So for example, for gases, as we said earlier, it has a lot of kinetic energy, very little potential energy, and that's why gases, as we learned about in CP1, they're very far apart. They have no fixed shape. They assume the shape of the container. And they have no fixed volume. They just assume the volume of the container because they're always moving in straight line random fashion. So if you look at this bottom right hand figure, the bottom one shows water vapor, and you notice that there's no attraction between the molecules. They're all just moving in different directions. Now with liquid, we start to have attractive forces because now they're holding the molecules together, therefore decreasing the kinetic energy, and this results in liquids having a fixed volume but assume the shape of the container, and they can flow. And if we look at the bottom right hand chart, we see that liquid, now we start seeing these attractive forces show up between the molecules. Now when we go to a solid, we have the predominant force is potential energy because the molecules are very rigid. They're not moving around very much. So there's very strong intermolecular forces. And this is why solids have a fixed shape and volume. So the reason that boiling points are generally high is because if you have a very strong attractive force, it takes a lot of energy to break it. And that's why anytime you go from a liquid to a gas, it requires a lot of energy because you got to break those attractive forces. So with phase changes, we have changes. All right. So with phase changes, we have some phase changes that are endothermic, meaning they require you to absorb energy. And we have some phases that are exothermic phase changes, which means they release energy to go to the different phases. So on top, we have the endothermic phase changes. And if you remember from CP1, endothermic means delta H is positive, so you have to absorb energy. So for example, if we have ice, it has to absorb energy to become a liquid, and so that's referred to as melting. And then when the liquid absorbs enough energy, it goes to a gas through vaporization. Now sometimes when you have a solid that has very weak attractive forces, when you add enough energy, it goes directly from a solid to a gas through sublimation. And a good example of this is dry ice. So when you take a chunk of dry ice out, it absorbs the energy, it goes directly to a gas. And so these are all endothermic processes. So they have to absorb energy to go from a solid, liquid to gas. On the bottom, we have exothermic. And for exothermic, delta H is negative. So that means it releases heat. And so when it releases heat, we go, for example, from a gas to a liquid, and that's referred to as condensation. A good example of this is if you've ever taken a hot shower and you have a cold mirror in the bathroom, so the steam from the shower hits the mirror, it releases heat and it condenses water droplets on your mirror. Likewise, if you get a tray and fill it with water and stick it in the freezer removes the heat from the liquid, causing the liquid to freeze into ice. So when you make ice, you're actually removing heat from it. Now, one thing that maybe trips up a few people is that the melting point and the freezing point are the same thing. So it's just depending on what you're referring to. So if we were talking about water, we would say the freezing point of water is 0 degrees Celsius. If we're talking about ice, we would say the melting point of ice is 0 degrees Celsius. So it's the same temperature, it's just depending on what phase you're referring to. If you're referring to the solid phase, it's called melting point. If you're referring to the liquid phase, it's called freezing point. But it's the same temperature, so that doesn't change. So some other types of phase changes is for deposition. So deposition means we go directly from a gas to a solid. And so on very moist, cold mornings, sometimes you get frost that appears. So frost is the deposition of water vapor to ice. Of course, vaporization, when it's really hot outside, it causes water to evaporate. Sublimation, the best example is dry ice. You can actually get some from HEB and play around with it. It's very cold. And so when we're talking about phase changes, we're talking about adding heat and removing heat. So here, for example, we have a heating curve of ethanol. And so what happens when we add heat to ethanol? What happens to its phases? And so you'll notice here, hopefully you can see that we have an A, a B, a C, D, and E. So each point represents a different phase or phase change of ethanol. So what's shown as numbers is the melting point of ethanol, which is negative 114, and the boiling point of ethanol, which is 78 degrees Celsius. And so we want to know, as we add heat, what phases and phase changes does ethanol undergo. So here at the A phase, since it's below the melting point, it's a solid. As you add heat to that solid ethanol, the temperature rises until it gets to the melting point. And at the melting point, which is B, we go from a solid to a liquid. And then when it becomes all liquid, as you add more heat, the liquid increases in temperature until it gets to the boiling point. So at point C, it's in the liquid phase. Now when we get to the boiling point, and now all the liquid ethanol gets converted into gaseous ethanol. And so that's referred to as vaporization. So once all the liquid gets vaporized into gas, then as you add more heat, the temperature increases. And so what you get on this type of chart is, or this type of curve is, you get slants and you get plateaus. And so when you're in one phase, as you add heat, you increase temperature. When you're going through a phase change, there's actually no change in temperature. So when ice is melting, technically there's no change in the temperature of the ice. What you're feeling is the effects of the surroundings from the ice absorbing the heat from the surroundings, which makes the surroundings cool. So when we have a phase change, we have a plateau on the graph. When we're in one type of phase, we have a slant. And that's important because we use different types of equations depending on which part of the graph we're in. If we're in a slant, we have one equation. If we're in a plateau, we have a different type of equation. So there's two equations that we're going to show you in just a moment. So this is more of a cartoon of what's occurring and this is actually a cooling curve. So we saw a heating curve on the last slide. A cooling curve is the exact opposite of a heating curve. So heating curve, we start at a low temperature, we go to a high temperature. Cooling curve, we start at a high temperature and we go to a low temperature. So again, you'll notice as you look at this cooling curve that on the slants, we're only one type of physical state, a gas, a liquid, and a solid. But on the plateaus, we're going through a phase change. So we're going from one phase to another. Now, the question asked is if there's no change in temperature, how do we determine how much heat is absorbed or released when we go through a phase change? And for every substance, there are particular constants that tell us how much heat per mole it takes, for example, to convert 1 mole of gas into 1 mole of liquid, or to convert 1 mole of solid into 1 mole of liquid. So there's these constants that we're going to talk about that can help us explain how much heat is needed to convert gas to liquid, solid to liquid, or liquid to solid. So here we're just showing you a simplistic version of a cooling curve. So here we start at some high temperature, we go to a low temperature. So for example, condensation occurs between points A and B. Because at A and B, we're going from a gas to a liquid. Because again, on the slants, if we start off on a gas, then we go from a phase change, gas to liquid. And then on the next slant, we're in the liquid phase. When we get to the freezing point, we go from a liquid to a solid, and then we end up as a solid. So freezing occurs between C and D. Now it's very important to know whether you have a cooling curve or a heating curve, because for a heating curve, heat will be positive. For a cooling curve, heat will be negative. So when you're calculating the heat involved in cooling something, you got to make sure you put a negative sign, because even the right number with the wrong sign is the wrong answer. So for cooling curves, we have negative heat because heat is released. For heating curves, we have positive heat because heat is absorbed. And so the way we know how much heat when we're at a phase change is needed to go, say, from a solid to a liquid or liquid to gas, are from tabulated, what we call standard enthalpy of changes. And this is in kilojoules per mole. So in your textbook or on a question, it's going to give you, for example, what's called the delta H of fusion, which is the amount of heat needed to melt 1 mole of solid into liquid. Also, you'll find in the same table the delta H of vaporization, which is the amount of heat needed to go from a liquid to a gas. And you'll notice that the heat of vaporization is always a lot larger than the heat of fusion, because at the heat of vaporization, we're breaking those attractive forces, so a lot of heat is needed to break them. Now, to find the delta H of sublimation, it's just the addition of the heat of vaporization and the heat of fusion. So that's if you're absorbing heat. If we're releasing heat, we have condensation and freezing. So the way you get those is you just take the negative of their counterpart. So for delta H of condensation, it's just the negative of delta H of vaporization. Likewise, delta H of freezing is the negative of delta H of fusion. So in a book or on a question, you're only going to be given the vaporization and the fusion delta H's, not the other. So you got to know to take the negative to get the other, delta H of condensation and delta H of freezing. So this is just a chart showing you the difference between heats of vaporization and heats of fusion. So you'll see things like argon and methane have very low heats of vaporization and low heats of fusion because they have very weak attractive forces. But when we go to things like ethanol and water and even benzene, you see that the heat of vaporization is very high. That's because those types of substances have very strong attractive forces. And later on, we'll talk about what type of attractive forces they have. Now, mercury has very strong attractive forces because mercury is a metal. And so that metal has very strong forces that hold those metallic atoms together. So now getting into the quantitative aspect, which is the main goal of this lecture this lecture is for depending on whether we're at a phase change or in a phase, we use different types of equations. So if we are at a phase, we're on a slant on the graph, we use this Q equals MC delta T. So if we're at a slant on the graph, we got to use this equation. Now this Q equals MC delta T should sound a little bit familiar. You used it in CP1, where M is the mass, C is the specific heat, and it's dependent on the phase. So a solid will have a different specific heat than a liquid. And then delta T, of course, is T final minus T initial. So again, if we're on a slant on that heating or cooling curve, we're going to be using this equation. Now, if we're at a plateau, we use the bottom equation, which is Q equals N times the appropriate delta H. So these are the only two equations we're going to need to calculate the total heat needed to heat or cool a substance. So the next few examples are actual calculations in calculating the amount of heat released or absorbed for a substance. So just to kind of recap, now we see a heating curve again on the slants. We use Q equals MC delta T, so this is for points these are for points A, C, and E. For points A, C, and E, which are on slants, we use Q equals MC delta T. For points B and D, we would use Q equals N times delta H. And again, N means moles. So we have to make sure we convert to moles, whatever we're using. So again, on the slants, we use Q equals MC delta T. On the plateaus, we use Q equals N times delta H. Now, for the Q equals MC delta T, it puts the energy in joules. For Q equals N times delta H, you'll see it puts the energy in kilojoules. So once we do our calculations, we want to convert joules into kilojoules. So this is a typical phase change calculation. We want to know how much heat in kilojoules is released when 45 grams of ethanol vapor is cooled from 118 degrees Celsius to liquid at 15 degrees Celsius. And you'll notice here it gives us the specific heat of the liquid, the specific heat of the gaseous phase. It gives us the delta H of vaporization, and it also gives us the boiling point of ethanol. So these are all things we're going to need to solve for how much heat is released. Now notice it says release, so that means our sign should be negative. So the first thing I always do on problems like this is I draw a little graph to help me show what types of phase changes are occurring. So on the y-axis we have T, on the x-axis we have Q. I call it removed because we're cooling the substance. So as we remove heat, what's occurring? So again, we'll start at 118 degrees Celsius. As we're cooling it, we have a slant because we're decreasing the temperature until it gets to its first phase change, which is the boiling point. And that's at 78.4 degrees Celsius. So we started at 118. So once we get to 78 degrees Celsius, we have a plateau. It's flat until all the gas is condensed into liquid. And then we continue to decrease temperature until we get to our final temperature, 15 degrees Celsius. Here on the graph. So we have three different regions. So in the top region, from 118 to 78, we're in the gaseous phase. But at 78 degrees, we're going from a gas to a liquid. And then from 78 to 15 degrees, we're in the liquid phase. So we're going to have three different Qs. We're going to have Q1 for the gas, Q2 for when we go from a gas to a liquid, and Q3 when we're in the liquid phase. So there are going to be three different Qs we're going to calculate. So Q1 is going to be the mass of ethanol, and I'll use ETOH as the abbreviation for ethanol, times the specific heat of the gas times the delta T of the gas. So it's just for the gas, the delta T. Now the second Q is going to be the moles of ethanol. Again, I'll use the abbreviation ETOH times, and now here we're condensing. So we're going from a gas to a liquid. So we're going to need the delta H of condensation. So that's step 2. And then in Q3, we'll take the mass of ethanol now here is the specific heat of the liquid times the delta T of just the liquid. So again, we have three different Qs. We're going to calculate each one, make sure they're in the right units, and then add them together. So now we're ready to plug and chug. I'm going to set them all up. Now remember, the delta H of condensation is going to be the negative of the delta H of vaporization. So we're going negative 38.6. And then Q3. So now let me work on getting the calculations. One second. All right. So we have 45 times 42. So the Q1 is going to be in joules because our specific heat is in joules. Q2 would be in kilojoules. And so now what I'm going to do is I'm going to take the joules and convert them to kilojoules. Top one should be kilojoule as well. So now we have all Q1, Q2, and Q3. We have them as kilojoules. So now we can find Q total. So we're going to add all three together. Let me double check my work. So here's kind of I like this one. It kind of incorporates Lord of the Rings. Come up with some interesting ones. So we're in Middle Earth, and Frodo found a new strong soft metal called Galvorn. It's actually, Galvorn is a metal in Middle Earth. I did some research. This metal was used to make armor due to its malleability. And then Frodo took this material to the wizard Radagast, and the wizard determined the melting point to be 125 degrees Celsius. And Radagast determined that it took 18.1 kilocalories to convert 5.75 grams of Galvorn solid to liquid. So how much heat is released in kilojoules when 186 grams of liquid Galvorn is cooled from 165 to 37 degrees Celsius? And it gives us the specific heats of Galvorn in the liquid and in the solid state. So let's see what Frodo found. So first we're going to draw a cooling curve. That's not a good cooling curve. So we're starting at 165 degrees Celsius. So as we're cooling it, temperature decreases until we get to the first phase change, which is going to be 125. That's its melting point. Now at the phase change, we're going to go from a liquid to a solid. So we have a plateau. And then after all of the liquid gets converted into solid, we're going to keep on continuing decreasing in temperature until our final temperature of 37 degrees Celsius. So we see we have from 165 to 125, it's a liquid. At 125, we go from a liquid to a solid, so that's a phase change. And then from 125 to 37, we're in the solid phase. So we have 3 different Qs to calculate. Now, Qs 1 and 3 are on slants, so we're going to be using the Q equals MC delta T. For Q2, we're at a phase change and we're at the freezing point, so we'll need the delta H of freezing. But as you notice here, it doesn't give us the delta H of freezing, but what it gives us is 18.1 kilocalories. It takes 18.1 kilocalories of heat to convert 5.75 grams of Galvorn solid to a liquid. So this is actually information about the heat of fusion. So from this, we can calculate the heat of fusion in kilojoules per gram instead of kilojoules per mole. So that's what I'm going to do first. I'm going to calculate the heat of fusion in kilojoules per gram. So I need to convert kilocalories into kilojoules. So the way we do that is 18.1 kilocalories times, there's 4.184 kilojoules in 1 kilocalorie. And so this will give us the heat in kilojoules. So we get 75.73. And again, we have to do this because it didn't give us the heat of fusion already. So now we take that 75.73 and we divide it by the mass, so the 5.75. And that'll give us the heat of fusion in kilojoules per gram. We get 13.17 kilojoules per gram. So now we know the heat of fusion. There we go. So now we can calculate Q1, Q2, and Q3. So Q1 is the mass of galvorm, which is 186, times its specific heat in the solid liquid state, times the temperature change in the liquid state. So that's 125 minus 165. Now Q2, we're at the phase change. And since our delta H of fusion is in kilojoules per gram, we just take the grams, 186 times the, now since this is freezing, we got to take the negative of the delta H of fusion. And then Q3, we're in the solid state. And now we can get the numbers. Remember, Q1 and Q3 are going to be in joules. Okay. Q2 will be in kilojoules. And Q3. Now I'm going to convert Q1 and Q2 into kilojoules. And now we can find Q total. So we get a final answer of negative 2,509.7. Let me just double check my work.